Okay, hello everyone again. Now it's time to start the second part of today's sessions, and it will be the lecture will be given by Professor Walter Friesenbichler, and it will be about the biology of polymers and the importance for processing.
Thank you, Miro, for the introduction. Welcome to everybody here in the lecture room and online. So, my topic today is rheology. And rheology, not only as a single scientific discipline, but in connection with a simulation and with the aim to develop products for real production and use in the company. So I go back to 25 years experience in my research work. And for me, rheology is the key to understand process. And simulation is the key tool to create digital twins of a process and all what we heard about characterization is the key to build up a digital twin of the material. And if we want to use artificial intelligence in future for our production of plastic parts, we need a digital twin of the material and we need a digital twin of the process. So I will focus in my talk, after a short introduction and motivation, to material data, not only the rheology, but also the other ones. And then I will show you industrial parts, which are already in production, which we developed with the company partners in our projects. And I want to point out the important influence of the pressure, which is mostly neglected in a simulation. I will show you how we can use a simulation with that excellent measured rheological data to find out the initial settings of a machine for a robust process with very, very low scrap parts. And finally, I show you what's up to date already now, that we, in the computer, we can find out a lifetime, a possible lifetime of a part in the later practical environment. So lifetime prediction. Finally, if I have time, I want to show you that the new topics for the future is to implement viscoelastic models into the simulation software. And then we are much more precise in our pressure predictions, and then we really can talk about a digital twin of a process. So, introduction, what's the market situation? Here you see the increase of plastic world consumption, and we're now, these are figures of 2021, published in 2022. The 2022 numbers are not published yet by Plastics Europe. So we have an increase for over the last 10 years by 4% as an average value. And the injection molding worldwide produces more than 1 trillion parts a year. That means approximately 5 million tons of injection molded parts per year are produced. High performance products, components, complex geometries, inline combined different material systems. And what we have in Europe is a constantly increasing cost pressure. That's because of low wage countries, a lot of production is moved to East and Far East companies and to Asia. That's an enormous problematic for our producers. If you look at the European plastics industry, we have approximately more than 52,000 companies here in Europe. In the EU, with 1.5 million employees and with a turnover annual 400 billion euros. It's big, is in the ranking the 8th important industrial sector in Europe. And if we look closer to injection molding and tool making, we have 35,000. It's more than the half. And half of the turnover is generated in EU countries by injection molding and the mold making industry. It's primarily SME dominated. And what we see that still now injection molding simulation is not area-wide used. And what is the challenge? The biggest challenge of our companies is the flexibilization in production. That means how to implement Industry 4.0, how to implement artificial intelligence, big data methods into production to cut down costs and to keep the production in Europe, not in Far East or in Asia. So, and if the companies develop, they have today use the so-called front-loading approach. And front-loading, nothing else means that we early address and avoid in the development typical faults. Here you see the costs over the development time for plastic part. So that is the current situation, the red curve. And a lot of costs arise if the mold is produced and the mold goes to the machine and then the mold trial starts. And then we see all the faults which we made in advance, and front loading means here we have a lot of money to spend. We shift the problems to the early development phase. Here we have to increase the costs, but finally we end up earlier with the development. So time to market is shorter and we cut down the costs. So that's what front loading means. And front loading demands a systematic and a multiple use of injection molding simulation. Without simulation, we cannot find out the problems which we would have been facing here in that phase. So the typical development process in a company is a so-called stage gate process with stages and gates acting like a traffic light. Stop here and rework or go on with the results. It's really gate meetings you can also cancel the whole product if the results will give you the information that it's impossible to produce a part, and cut it early and save money. And typical is the idea is fixed, and then the first group, the planning group, starts with the obligation book of the part. That means all the specifications which we then need for the running parts in their life. If this is fixed, another group starts with the part development, with the geometry of the part. But not only the design is important, but also how to produce it, the technology. And first 2 or 3 possible materials. And in that phase, we make a so-called design freeze. We say the design is fixed and the material category is fixed. And for that, to cut down this uncertainties, we use a first couple of simulations. Then, after the design freeze, we have to develop the mold, the process, the machine or the system, and we have to do another type of simulations. Not only a simple feasibility study simulation, but we have to do a precise injection molding simulation of the inflowing material, but also a mechanical characterization and simulation. And finally, we end up also in that phase with a lifetime prediction. Because then we are sure, yes, we can produce it, we can earn money, and we have a benefit. And the fourth phase is then the phase preparing the start of production. And here we have a closer look to the process, to the machine settings, to quality, which we have to obey, and then finally starts the serial production. So that's the whole story, how we came from the idea to a real plastic part being produced. And out of projects where I have been working since 2003 in Europe and in national projects, we found out that cost saving potential is up to 25%, sometimes up to 65%. If we change from a mechanically produced part with drilling, milling, and so on to an injection molded part, and with time savings and marketing advantages. And these numbers came out of the project from the companies and their experience. So that's what we can gain if we use a systematic development and if we use simulation, but not only flow simulation, but also structural mechanical simulation and lifetime prediction. And what we then did 2 years ago, we used such simulations according to a DOE, design of experiments, to learn an artificial intelligence quality controller how to control the machine that we have no spare parts anymore. That all what is produced is within the tolerance level. And it was a 4 years project with all these companies in Austria, and we really succeeded in running such a quality controller based on convolutional neural networks. And without stimulation, it would be much too costly to adapt a machine with such a controller. So we used a huge simulation set for the first training data for AI. And then we used really, according to a DOE, we used practical experiments, but not more than 30 to 35 real experiments. And then the controller worked. So therefore, I think it's worthwhile to talk about quality of material paper, quality of viscosity curves, and how to use it finally to speed up the development and to cut down the costs. So that's what we all know. In precise data, we call it garbage. You put in, this is the simulation, best simulation software ever. You can only get out garbage, which doesn't fit to reality. So therefore, we make simulations. And if you have used a simulation software, don't talk about a specific one. We have first a so-called geometry check, where we in colors show the different thicknesses of the part. And we all know as plastic engineers, if the thickness very thick and very thin, then the problems is warpage with shrinkage. So this is a first check to find out weak areas. Next, we make a filling simulation, and the outcome is such a picture where you see that gray areas are the filled parts at the end of the filling. And then you see, oh, here we have a problem with a weld line. Two molten streams come together, and then they are welded, and the factor is not 1, but below 1. So it's the area where possibly the part will break. Yeah. And finally, we can make in a full simulation where we not only have the filling time, the weld line, entrapped air, for instance, the pressure which we need the melt temperature, frozen layer, and so on. Finally, we look into the real shrinkage. And here you see, this is a metal part. And if the part shrinks and warps, the metal part is moved inside. And if you here have the copper connection, they possibly can break. So therefore, it's important to make a simulation until the final virtual part, so that you can see if this geometry fulfills the specification. The gray one is the mold cavity, and the colored one is the part, but in the computer, in the virtual phase. So, and here you see now viscosities. Look here, water immediately changes with a 1 Pascal seconds. It's a low viscous liquid. 10 Pascal seconds, you see now it changed. But here we have our thermoplastic melts. It starts to ramp down now after this time. And here it is on the upper side. And our zero shear viscosity of the polymers is 1,000, 10,000 for rubber materials, 100,000. So you see, we need high pressures. Pressures of 1,000 bar in rubber injection molding, 2,500 bars. To press this high viscous material through the runners into the mold. And that's what we have faced. So water is a Newtonian liquid with always the same viscosity. But in thermoplastics, we have a problem. And therefore, we use this capillary rheometer and combat plate rheometers. They do big ones, which we use. And it's very simple. It's like if you get a vaccination by a doctor. We have the material, we have a piston, we press the piston down, and the liquid comes out through the needle, or in our case, through the die. And what we measure is from the piston speed, we get information about the shear rate. And from the pressure, which we measure here, we get the information about the shear stress. Shear stress and shear rate we combine to a viscosity, point by point. That is under pressure, high pressure capillary rheometry. And the other method is we have a pressureless method. We have two plates, and in between we have our melt. Then the upper plate can rotate and applies a shear rate, or it can oscillate. And then we find out G prime, G double prime. I remember to E prime and E double prime from Rebecca's talk. Then we find the storage and the loss moduli of our liquid material. And with that two methods, we finally, and we measure it in minimum 3 different temperatures. We then measure such a viscosity curve that, look here, it's 8 decades in frequency with 4 different rheometers. So it's costly. But here you have the cone plate measurement in steady state rotation, and the blue ones in oscillating mode. And we need both to find the zero shear viscosity on the one hand, but to come to higher frequencies so that we have no big gap in between the data which we measure with the capillary rheometer. If we have here such a gap, the simulation, the approximation software don't know how to make a curve through all the measured points. And the computer doesn't need measured values. The computer needs an approximation curve. we tell it's a material law. It's part of a so-called material card where all our testing results are in. And with that, we nicely can characterize the flow behavior. But then we made a measurement where we applied a so-called counter pressure against the outflowing melt. The piston pushes the melt down, and we have a counter pressure. And if we raise the pressure by 100, 300, 600 bars, you clearly see viscosity goes up. And that happens in injection molding with 1,500, 2,000 bars. So we compress the material, we increase the viscosity, and if we have a pure viscous viscosity law without this behavior, we cannot say that we have a precise result from our simulation. So we need the pressure influence. And here you see the Barrow's equation. It's an exponential equation. So this term can, you will see it later, it can go up to 4,500. So at high pressures, the viscosity is not, let's say, 1, but 4,500. And that's difference for processing. And if you then make a simulation and you say, okay, all is fine, we can produce the part, and then you go to the machine with the mold ready, and then you find out, I can't heat my part. I have a big problem because I spent 50,000 euro for the mold, and now I cannot produce. With that knowledge, you can find it out earlier. The next what we need for simulation is a so-called PVT diagram. P means the pressure. We measure from 200 to 1,600 bars. V means a specific volume, is the reciprocal value of the density. And T is the temperature. And here we have the nice information what happens if we start with the injection molding at melt temperature 200 bars, then we go up to 1,600, and finally, if we demold at 50, we should come to that point. And in between, that's the process. How I make the process setting. So this is the information what happens with the material during solidification. And the computer needs such functions behind that he can calculate a virtual part, the final shape of the part. And you see, if it's not filled, black curve. If it's filled with talcum increases the crystallinity, is a nucleating agent. This throws the temperature for the starting of freezing of the crystals is shifted to higher temperatures because the crystallization starts earlier. And if you go here, this point, and see the temperature, and then you go to 1,200 parts, go down, then you will find here delta T. And in between are 1,000 parts. So easily out of this diagram, you can find out how much temperature increase you would have if you increase by 100 parts. It's 1.5, 1.7 degree per 100 bar, only if you compress. And that's important for the processing. And we measure this with a so-called PVD apparatus. It's a piston type machine. You have a sample. It's a rod. You put it in. You have the sealing here in between upper and lower sealing, and then you apply the pressure. And then you start at a constant pressure to cool down this material. Then the piston goes down, down, down till the cooling. And with measuring the deflection of the piston, you find out the volume. So It's an easy method, a bit tricky to have the sample without any air bubbles. Otherwise, and another point is frictional forces. What we then need, we need for the heat exchange in the mold, we need the thermal conductivity. But in most cases, people say, okay, we measure it pressureless. For the melt, we take this value, and for the solid, this value. Here you see, we measured it at elevated pressures. Look how thermal conductivity increases. If you compress the material, the molecular chains are closer to each other. So the heat transfer is increased. If you don't take this into account, your frozen layers from the cold mold wall, in a runner system, melt is hot, goes into a cold mold. Mold can be 50 degree, 25, 250 degree melt temperature. Then from the boundary, from the cold mold, it freezes to the, and if the thermal conductivity is under pressure higher, it freezes faster. So the outcome finally is, if you take these values, you say, okay, I can fill my cavity, but this behavior is in reality. And the material freezes from the cold mold walls much faster. And we had several examples that then the people could not fill. Simulation said you can fill, but if you put this data in the simulation, you can't expect that this situation is covered then. That's what I always say. We need precise and close to the practical process measured material data. Then simulation is good. And this pressure influence of the viscosity, you can take a capillary rheometer. What you've seen before is that sketch. Now you put a so-called back pressure chamber here, and with that you raise up the pressure, and then you force the polymembrane through the die, but here you have 300 bars. And then you measure these values which I have shown you. And we did it also on an injection molding machine, but that's not so important. Now to the effect. I showed you that's an exponential equation, and this exponent is that one which we are interested. And if you make a division, the pressure-dependent viscosity divided by the viscosity without taking into account the pressure, you have such a shift factor. And the shift factor is nothing else than this function, e power to beta times the delta P. And that's, if I plot this AP here we see the viscosity, here we see the increase, polystyrene and PP, and here you see the values. So for PP, if we go to 1000 bars, pressure is 11 times, viscosity 11 times higher. If you go to 2000, 121 times higher. But for polystyrene, with this complicated monomer with the styrene ring, if you go to 2000 bar, it's 500 times, and to 2500 is 2590, really 2500. That's pressure influence. We have to take it into account. We have to measure it, but mostly the bosses say we have only a limited budget for material characterization, and this is too expensive. No, we do it like all the others. Then you are not better than all the others. And yeah, that's the story. Here you see the measurement which we did on the injection molding machine. That's polystyrene with the increase, and that's polypropylene with the increase. You see, Yeah, that's reality. And if you don't measure this, you are not. You're far away from reality after the simulation than the others who spend more money on that. And that's part of the story of front loading. Put more money in the early stages of the development, do all this material characterization, then you will find out a lot of faults which you later have to correct, and then in total with all that activities, that's not so important. You are much better. In one of the PhD thesis of one of my students, I told him, please look into literature. I want to see what is in literature in terms of beta values, pressure dependence. Look here. It starts Maxwell and Young, 1957, 1968, 1983, 1962. That you can all find in literature. And now I have put it together into this table for the polyolefins. And here for ABS, polycarbonate, PMMA, PS, yeah, you see, there are data available. You must pick it out from literature or take it from this. And then you can implement it into the software. And then you are much preciser in the simulation. So therefore, I made this collection of data to show you it's not always necessary to measure it. If you have a certain PC, if you don't want to measure, take value of 30. You're much better than taking nothing. So that was the first part, to show what we have to do, what is costly in characterization, but we have a benefit. And how big the benefit is, I will show you now. These are industrial parts in production. First, the influence of pressure. That's a mold of the plastics processing institute in Leoben, built by Engel, and we produce such boxes, stacking boxes. And we have two pressure sensors inside. We made a multiple simulation with and without this pressure coefficient of viscosity. And for the P2, which is very critical, but because it's far from the gate is here. You feel in the material here in the middle of the bottom, and here is the long flow legs. Blue is simulating without pressure coefficient. You're in that case 100 bars higher, and the measured pressure, and that is the pressure with a simulated cavity using the pressure coefficient. You may think that must be the opposite way around. This high simulated pressure comes because the simulation without pressure does not take into account the mold diffraction. Under high pressures, the mold, the steel deforms elastically. And here with the pressure coefficient, we are closer to the real situation. The next part, that is a real part which use the dentist in his system for drilling our teeth. And it must be lightweight because the dentist works 8 hours with that thing in his hand. And therefore, the company W&H decided to move from metal to polymer. And here we have a very thin-walled bush made out of syntactic polystyrene with a wall thickness 0.4 to 0.8 millimeters, very thin. And the filling pressure in the production was 2,350 bars. And with the first simulation, we did not succeed. Then we went into the lab and measured the viscosity curve at 1000 bar back pressure. You see how high the difference is. And out of this measurement, we got this beta value. We implemented it into mold flow. And that was the mold flow simulation without taking into account pressure dependence. The simulation said, oh, can nicely be filled. You need for filling it nearly to 100%, you need roughly 1,300 bars. Exactly on the production machine, the company needed 2,350, not 1,300, 1,000 bar more. And with taking into account the pressure coefficient of viscosity measured by our lab, we came to 2,368, only a difference of 18 bars. But they were really surprised. But for thin-walled parts, taking into account the pressure effect is essential. It's very important. And outside, mostly the people, the simulation engineers, they don't cooperate with the plastic engineers. They make the simulation and then they make this. But the company needs that. 85% higher. Okay, now what can we do finally if the design and the mold is ready for production? We make a so-called VARIMOS, virtual and real injection molding optimization system. That is short, VARIMOS is short for that. And what we can do with the simulation, we build up a DOE, design of experiments. Then we make these simulations according to the DOE as a kind of automated simulation in the computer. And finally, we get out, if you say, okay, we want to have 32 simulations, we get 32 parts. We made with the ITV Aachen projects, they made more than 218 simulations because they made a variation according to a very large DOE. And then you have in the computer these virtual parts with all its shape and all the dimensions. And then you say, okay, then these are the results. Now I have to make an optimization, linear or non-linear. And finally, they wanted to know which machine settings in terms of mold temperature, melt temperature, pressure, packing time, and so on. Which settings do I have to choose that my part will be perfectly produced? I do it in the computer. And with all the knowledge which I told you, you know now it can't be exactly the reality, but it can be close to reality. And it is different. Then the process engineers of the machine, they will switch a bit the setting and then they can produce. And then you really, you save a lot of money in terms of days by days making more trials in the lab with a production machine, which is costly. Okay, then we have, look here at the diameter, length, and the warpage, independence of process settings, holding temperature, mold temperature. And if you do the DOE, you find out over the whole area, these within the green area are the good parts. Outside there are the bad parts. And then the software does this. finding from all the quality criteria where all the criteria has good parts. That's the area which is gives the best results. And then they build up an optimization. And what the computer finds out, he finds out in the room such curves where the quality is good and not outside, upper and low, but on this surface you have good quality. And what the system automatically then does, the system now wants all parts which are inside of the tolerance range. They want to find out the conditions that all are in the middle. That's perfect, because then I'm safe in terms of outside influences. I'm safe for a certain change of material, a lot, and so on. So that's what the computer can do. And this we did with such a part. I told you yesterday, Magna. It was a PET, glass fiber fill, 35%. Oh, I'm roughly at the end with my time. DSM was the supplier. We measured by our own all this data. And then we found out the green data came from DSM. Magna said, no, we do not want to spend any money, any additional money. Then I said, we measure it in our lab. And the blue curves we measured by our own. And with the transition temperature was suggested from DSM with 260, but out of the DSC we found it's 250. Then we changed it, and then we got this result, the optimum of the simulation, and a 62 days mean value of the running production. There's nearly no difference. That can simulation do. And in terms of quality results, we had the part weight and 2 diameters. Look here, and the cycle time. There is still, the cycle time still can be reduced. But look to the diameters. They are close to each other. So that was the simulation result. And I think lifetime prediction is very interesting. Do I have just 5 minutes? Yeah. Because that's really state of the art. In lifetime prediction, we integrate process simulation, injection molding simulation, with structural mechanical simulation, with measuring mechanical data, notched, unnotched, and put into motor oil for a certain time at different temperatures. And we use that for stress analysis. And finally, we get from the injection molding simulation, we get the fiber orientation tensor, because that's how the fibers really are placed in the part. Then with that, we get a stress distribution over the part with the fibers in the position like the simulation says, and then we make a lifetime estimation, and we did it for this part. It's for a car mirror, and it's a lens holder. The green is the part that holds the lens in the car mirror system, done by Zitzala in Austria. And if you drive a car, you always have this up and down of the forces, and you have this dynamic loading. We made injection molding simulation. We found that filling time. We found the weld lines, and we found out the fiber orientation. And this was implemented into structural mechanical. simulation. Then we built up in the computer these cyclic stresses, and we calculated the lifetime, and the software, the FanFAT software, it's a commercial software. We found out on the position 1, the part can fail after 120,000 cycles, and position 2, 56,000 cycles. And that's the critical area with the position 1 and the position 2. That's coming out of the computer. Then the colleagues make the testing, real testing under this dynamic load. I can't show you the movie, but then the cylinders move, and finally you have, after 120,000 cycles, you have to brake. And here you have the comparison, simulation, and test. And here you see position 1, position 2. You have to brake exactly at the point what the simulation said. And that's really a very, very important topic. So, and I will stop now here. That's a very complicated topic, viscoelastic modeling. I show you only, You measure with the cone plate rheometer, dynamic modulate, G prime, G double prime. Then you set up a so-called spring damper model, Maxwell model, but with 8 elements. And out of these measurements, you can find out the elongational viscosity, the first normal difference. Then we made real experiments with the injection molding machine. We have different conical dies, and that's the simulation result. With a cross model, the model calculation says you need 70 bar to inject through this open nozzle. And these 2 points were the measured points. Then we said, okay, we have to take into account viscoelasticity. We came up to 370 bars. And then that was Professor Mitsoulis from Athens. Then he said we must implement the pressure dependence. And then we ended up with this simulation, being very, very close to the practical values. So what I think is in future, we should implement such viscoelastic models and Moldix 3D. The faculty uses Moldix 3D from Taiwan. They already have implemented it. I initiated a project that SigmaSol currently is implementing these models. So, and I would say in 10 to 15 years or 20 years, in the case of quantum computers in the big companies, you can take all this into account to get real digital twins. And with that, I want to finish. Thank you very much. Yeah. I think it's not necessary. A lot of companies were inside in this project. So thank you very much. I think we shall. I will like to answer questions on that.
Okay, thank you very much, Walter. We continue now. So we continue now with thermal characterization of polymers, which is, of course, also very important. I will start with small introduction. And, I will talk just about 2 thermal characterizations, so the DSC and the TGA. Thermal analysis method are used to determine some physical chemical properties of materials during heating or cooling, or if we leave them at a certain temperature. changes in material are usually shown as a function of temperature or time, and physical properties that we can determine are especially glass transition and melting temperature. These are two most important for polymers. Polymorphic transitions are not so much. It's more in organic chemistry or so in biochemistry. And we can also measure some liquid crystalline transition. And chemical properties, we can determine decomposition or pyrolysis or oxidation stability. And we can also follow, for example, some reaction of polymerization by using, for example, DSC. So here are the 4 thermal characterization techniques. We already heard something about DMA. TMA is another one, but there is no time to go now into the details. So as we see, there are many tests we can do, and some techniques are more suitable for some and other for the others. So first, let's talk about DSC. I think this is the basic thermal characterization technique in polymers. Yeah, and it measures the amount of energy which is or consumed or released by a material while we heat it, cool it, or maintain it at a certain constant temperature. So we have some heat flows, specific heat capacity, and heat rate, dt per dt, and we have this last part is a time-dependent response due to the temperature. We have 2 types of DSC. One is power compensation DSC on the left, and on the right we see heat flux DSC. They both, I can say, give us more or less the same results, but both techniques have some pros and cons. For example, here with power compensation DSC, I was never very pleased with baseline stability, which is much better in heat flux DSC. But usually, I think results are more or less the same that we can obtain. There are also variants of DSC. So first we have this conventional DSC, which is usually used, and you can see it here on the picture on the left. Then there are new cheap DSCs, which can use very high heating or cooling rates. Here it's a picture in the middle. It's also in our lab. It's called flash DSC. And here we can heat the samples with a rate of 40,000 kelvins or degree per Celsius per second. So very fast. Cooling is a bit slower, but it's still, I think, 4,000 kelvins per second. And the third DSC is high pressure DSC. Here we can follow, for example, some reactions that are going on under high pressures, and also if there are some, for example, some curing or phenolic resins, it's useless to make DSC because of the vapors that are released, and so for phenolics we have to use this high pressure DSC. Some equipment can also work in vacuum. Applications, we usually measure glass transition temperature, melting temperature, heat of fusion, crystallization, degree of crystallinity, chemical reaction. We can follow the kinetics. Then, of course, specific heat capacity is very often important, and oxidation stability is also determined by some standard for some materials. DSC has to be calibrated always and each, and we calibrate temperature and enthalpy. And for this, we use some usually pure metal standards with very defined melting temperature and enthalpy of fusion. So this has to be checked more or less often depending on the system, but
Some clip now, they on the up.
okay. Okay. No, this is standards, yeah. So measurement, DSC measurement for polymeric materials, we usually follow this standard ISO 11357. There are 8 parts of it, and all determine some different things. So about hints and tips. Sample mass that we measure is usually somewhere should be between 5 to 20 milligrams. Depends on the test and on the sample. So sometimes we have to decide to take some more, sometimes less. And it's recommended that we make at least 2 parallel measurements. And if we do that, we have to try to have the same mass of the sample. So as much as possible, plus minus, for example, 1 milligram is good. If possible, the samples must be flat and thin. That's how we ensure a good heat transfer from DSC to this aluminum pan, and from aluminum pan to the sample, and that's how also we get reproducible results. Usually we use nitrogen for purging cell. Heating rate is 10 to 20 kelvins per minute. Higher rate we get better sensitivity. So some small transition we can observe them. With small heating rate we cannot. But with lower rate, we get better resolution. If there are, for example, 2 transitions very near to each other, if we use fast heating rate, we will not see them as a 2, maybe we see them as a 1, or maybe like a shoulder, for example. Then we had to heat a sample to a temperature which is high enough to erase thermal history of the sample. So what is thermal history? Polymers are, for example, thermal behavior of polymers is sensitive, for example, on processing condition. We cool it faster or we cool it slower, we will get different DSC data if, for example, the material is crystalline. Then, of course, sometimes we measure a part and which was left, which is 10 years old or something. And this, what was happening, we can sometimes see on the DSC. So this is so-called thermal history. Then we hold it at this melting temperature, then cool, and usually we heat again. And at the end, it is very good, very useful if we reweigh the sample, so we can see if we had some weight loss. Because if we had some weight loss, it means that maybe our sample was humid, or there were some solvents remained inside, or there was a degradation of the polymer during the heating. So this sometimes can give us some better insight also in the measurement that we made. So this is, I can say, like a curve for teaching. This is how the DSC of PET looks like usually. We have a glass transition, we have cold crystallization, melting point, and if we go too far, the degradation. So this is, these pictures can look also in reverse. So glass transition goes up, cool crystallization down, and so this type of showing is according to ICTAC recommendations, but I must say some use it, some use reverse, so it depends on the system. So now if we go to the glass transition, Usually TG lies in the middle of this region. It's a region. It's not really instant point. So sometimes you see the glass transition determined for on two decimal places. I mean, this is really nonsense, but can be also observed. This glass transition is sometimes hardly visible. If we have crystalline polymers, for example, or phenolic resins, sometimes or composites with a lot of filler, and especially if it's crystalline polymer, we will never observe this glass transition temperature. We have to use DMA for that. Why we cannot see it on DSC? Because glass transition is a transition of the amorphous part of the polymer. So if we have a polymer which is 50% crystalline, there is only 50% of polymer that gives this signal, and that's why it's sometimes very hard to see it. So this is how we determine it, and usually it is in the middle. And what we usually calculate together with glass transition is also this change in heat capacity. And for measuring glass transition for amorphous polymers, we usually use higher heating rate, 20 kelvins per minute. Also for crystalline polymers, if we want to see it really glass transition, we usually then have to increase this heating rate to 20. Otherwise, for melting, we use 10 degrees per minute. Then we have cold crystallization or crystallization. Crystallization peak is the peak we obtain on cooling. From high temperature, when we go to low temperatures, we see some exothermic peak. And cold crystallization is something we observe on heating. So we heat the sample and the crystallization starts because this is very usually observed in PET, because PET crystallizes slowly. And so if we cool the melt fast, it will not crystallize. But once we start heating, we come to a certain temperature which enable enough movement of molecules to start crystallization. We get a crystallization at, let's say, 120 degrees. So it's not really cold. It's at 120 degrees. It's quite warm, but we call it cold. So we see, we measure here enthalpy and peak temperature and so on. We can determine also crystallization, kinetic of crystallization, which we can do isothermally or dynamically. So during the cooling, or we just cool fast to a certain temperature, for example, like here, 124 to 120 degrees. Dynamical measurements are usually faster, and isothermal is the problem is that it's usually can be performed in a very small temperature range. And even here, when this crystallization is slow, here the sensitivity of DSC is also questionable in this region. And so mistakes sometimes, but it can be easily done. And this is dynamically we heat with we cool with various cooling rates, and we observe those curves, and from these curves we calculate the kinetics. Kinetics of crystallization usually follows this Aurami equations. We have this constants N and K, which characterize the nucleation time and the crystal growth geometry. However, Aurami equation has some limitations, and those, for example, this N should be always an integer number, so 1, 2, 3 till 6, but usually we observe something like 2.4, 3.6, or something. Because crystallization is more complex than this Aurami predictions, we have secondary crystallization in polymers and crystal perfection. So crystal becomes better and better and bigger actually. And this is all, at the end we also see that on this picture, and it changes a little bit. But however, generally speaking, this Aurami equation gives us quite good results. About cheap DSC, we can use it to study a crystallization in a wide temperature range and cooling rates. So here we are not limited to, we want to do it isothermally to a small temperature range. We can cool it by 4,000 degrees per second to let's say to 150 degrees, and we can use this also to cool it to, let's say, 80 degrees. So we have a few decades of temperature we can measure. Here you can see this was it's a peak. There were various heating grades, cooling grades. I think this was the faster was something like 1,000 degrees per second, and this was more normal 60, I think. This can be also used, for example, to study size-dependent properties for nanoparticles, for example. So this is what we here we see there. And also we can study some fast reactions which, for example, almost like explosives, and so we can do then, for example, melting point. Some material starts to they don't melt. They start also to degrade during the melting, and so we cannot really have data about their melting, and with this fast heating, we can separate melting from the degradation, because degradation is comes a bit later and slowlier. Degree of crystallinity, I said a few times, it's very important property of polymers because it influences mechanical properties. This we usually measure at the heating rate of 10 kelvins per minute, and we calculate the area under this heat flow during the heating, and then we use this equation to calculate the crystallinity of polymer. However, we need here this H0. H0 is usually calculated value of perfect crystal. As I said yesterday, there is nothing such a perfect crystal as in polymers. We can come very close to this perfection, but usually not. So we have some values, and this value we put into the equation, and we calculate the degree of crystallinity. Those data can be found, for example, I took them from Encyclopedia of Polymer Science and Engineering. Also, they are sometimes published also in articles. So about application, there are two things. Usually we measure that we heat the sample twice. So we have first heating and the second heating and cooling in between. First heating gives us data about the thermal history of the sample, and sometimes from this we can also predict the reason for the failure of product after some specific conditions. And so first heating is it's not a material property, it's a property of finished part. Let it be, it can be granular also, it's not a part, or finished part, for example, some whatever. And the second heating gives us data about material, about the polymer. So here we can distinguish, for example, between two batches. So one batch can be good, one batch can be bad. We can compare those and see the differences which might then show us possible differences also in, for example, or in chemical structure or in molecular weight distribution, and so on. And all these parameters influences the properties also of finished part. So if we compare two materials, for example, we take some lenses and make a measurement, and we see differences in this part. We see that material was not the same. It was a different material, and maybe that's why we have problems maybe during production or maybe during the use of this part. Then there is another technique, it's called modulated DSC, various these abbreviations. This we can use to determine hardly visible effects. Sometimes it's, we know there is something going on, we don't know what is going on because the DSC curve is complicated, especially if you have some blends of polymers, and so then we use modulated DSC. This technique is more slow, so it takes a lot of time. How it goes, we have an average heating rate, which is usually less than 5 degrees per Celsius. And on this, we apply sinusoidal modulation of temperature. We can do it so we have only heat modulation or heat-cool modulation. So it goes down below this average and so on. The problem is here to determine the right conditions to do this modulation period and modulation amplitude. So, yeah, but with some experience, if you do it several times, you can get, let's say, usually quite good results easily. Otherwise, you have to select a bit different conditions. So the signal we get is something like this. So this cannot really be used. But then after a bit of mathematics, we obtain irreversible heat flow and reversible heat flow. And this is the total heat flow, which corresponds to the normal DSC measurement. Normal, I can say that it's not really totally normal, because this is usually taken by small average heating rate, smaller, not 10 degrees or 20, but maybe 2, 3, or maybe 5. So it's a bit different than normal. So this method enables us to separate signals which are reversible by nature. So heat capacity, if we cool it, if we heat it, it changes. But if we cool it, it changes back to the first value again. So we do that 100 times, it will always be, it's reversible. Melting, once it's melted, okay, it's we cool it down, it will crystallize. But there are irreversible, something like relaxations. When we prepare materials, and for example, we use injection molding, there are always some stresses inside. We can see some relaxation also. Relaxation after this glass transition, for example. Then we can see the recrystallization and cross-leasing, disintegration. So the things that will not go back if we cool down a little bit. Once something evaporates, it will never come back for sure. And this is how we really nicely separate. For example, here we see glass transition temperature and melting and recrystallization as well. There is a two-layer film of PET and polycarbonate, and here we see total heat flow in the middle, And we see there is a difference between the flat area before and after this peak, which tells us that there might be some glass transition temperature because of the steep change. However, this peak is not, it's hard to say. But if we use modulated DSC, we see nicely glass transition and some fold crystallization it was here. So much about the DSC. The second method is thermogravimetric analysis. This measures the change in mass, which might be a loss of weight or a gain of weight as a function of temperature in time. Yes, also material can gain some weight. For example, if you do measurement in oxygen, it can oxidize. Takes oxygen and it will be heavier than before. So the device consists of oven, very precision balance, and atmosphere regulation system. So we can use various gases. Most commonly, we use nitrogen as inert atmosphere, oxygen, or air as well. Why do we use it? Determination of moisture or solvent content sometimes, which is moisture is quite often a problem as well. Determination of filler content or organic phase in inorganic, determination of type of polymer and the composition of polymers, thermal stability, the composition kinetics also, and therefore we can determine the lifetime of material and of course also oxidation stability. Measurement sample mass is usually from few milligrams to few grams. However, not with one machine. There are some special machines where you can use few grams. However, if you work with, for example, composites, it's good to have equipment where you can measure at least half a gram, just to, for example, to determine really the right quantity of this filler in a composite or so. Atmosphere, nitrogen oxidizing, heating rate usually up to 10 degrees Celsius per minute. And of course, we can add some FTIR or mass spectroscopy at the end. So we can determine also structure of product, degradation products, for example. And sometimes vacuum can also be applied, which might be important, especially for rubbers. If we have a rubber and make TGA, we will get the composition start or losing of weight at maybe 200 degrees or something, or even before. But it's not really a degradation. We just lose some these plasticizers and things that are in, which are liquid, and they evaporate actually. But then we cannot distinguish what was evaporation and what was degradation. And then we can apply also vacuum. Vacuum reduces the boiling point of those liquids, and so we can separate those two peaks. Then it's also important this sample mass and how we prepare a sample. And here is the result of graphene oxide, a very recent result. We heated it by 5 degrees per minute. And when we put in a particle of 3 milligrams, just one single particle, actually it exploded. And we see this hard weight loss. And it's hard to believe, but sometimes people show these results as a normal TGA and they talk about that. They don't realize it was explosion actually. And if we grounded this powder particles to smaller particles powder, we get this red curve, and it's nicely we can see follow the degradation. So it's important also how we prepare our samples. Then TGA has also, not everyone has this DSC sensors. So one way we follow weight loss, and on the other hand, we follow what is going on with the enthalpy. Is it exothermic, something that's going on, or endothermic? So here we see the melting and then degradation, oxidation at the end. And however, I must say that this signal, it's not so good to be used as instead of DSC. It is nice approximation, I can say, but I wouldn't really recommend to use it instead of DSC. There is also one possibility, it's high resolution TGA. So this helps us to separate some weight losses and different steps in degradation to get better insight into this. This is conventional TGA, increasing vinyl acetate. We see that the more vinyl acetate we have, the more it degrades in this area, about 300 degrees. So from this we can actually see how many percent of TGA of vinyl acetate we have. However, it's very hard to put a border on this curve. So we can use this dynamic measurement, which reduces. We just put their data, we define the maximum rate where it weight loss rate, and then the heating rate reduces. So we get much better picture, and we can easily separate and determine the structure of those copolymers. Then, of course, we can determine thermal stability of polymers. Here we see that polymers degrade at various temperature range. However, I must say, for example, PVC, if we look at it here, it should be stable until 250 degrees. However, it is not. This depends on the rate of the heating rate. So if we use 10 degrees per minute, we will get this type of curve. If we reduce it to 1 degree per minute, this curve will be more here like PVDC. So heating rate is quite important. There is another picture which shows mass loss of EPDM with various degrees percent of polyethylene, and we see that also the degradation proceed according to this copolymer content. Polyethylene is much more stable, less stable. Zero, yeah, but more stable than this propylene. Then one thing we obtained from TGA is this first derivative of weight loss. This is actually the rate of decomposition or rate of weight loss, and this can also give us some data. First, we use this to better determine the decomposition steps. If we have several steps, now we see it here, we find where to put the borders. It's much easier. If you look just on the weight loss, it's hard to put to make sometimes to make these borders. And this was PMMA, polymethyl methacrylate, and this gives us information also about the chemical structure of polymethyl methacrylate, because this peak at 150 to 200 degrees corresponds to the quantity of head-head bonding in the polymer. So this polymer had a lot of imperfections, so head-to-head bonds. This is the second peak at 300 degree corresponds to the double bonds. So the termination did not proceed with coupling of two, but with disproportionation. Irina was talking about this yesterday. So there are double bonds, and those double bonds are again weak point in the structure, and it degrades about around 300 and about around 400. This is a normal degradation of polymethyl methacrylate, where methyl methacrylate is evaporating. So from this, we actually observe also chemical differences in chemical structure. Yeah, said those. Determination of filler content, that's also very often when we work with composites. We can do it in two ways. We can make analysis in oxygen atmosphere, so we burn everything what is organic, and what is left is our filler. Or we do perform the pyrolysis and then switch to oxygen and leave it there till the end, maybe 20 minutes, usually 30 minutes is usually enough. So if we do the measurement only in nitrogen, then some polymers degrade 100%. So we will obtain the what is left here on the left side of the picture. This is filler content. But sometimes some polymers do not degrade. It's char is formed. That's why we have to do the decomposition also in oxygen atmosphere. However, we have to be also careful. Once we obtain after this TGA analysis, we get some powder in our crucible, and then we usually, it's good thing to do is to measure FTIR to see what this filler is. Sometimes we see it is calcium oxide. However, it is not calcium oxide, it's calcium carbonate, which degrades at high temperature into calcium oxide. So we have to use this also. Be careful to calculate the right quantity of filler content. Estimation of polymer lifetime, it's also very important, especially if our polymer is used in some rush environment at a higher temperature. What we do is we measure the composition with at least 3 measurements with 3 different heating grades. So there are 5 different heating grades there, and then we determine the various decompositions, and we calculate from this activation energy, and usually it is 5% that we take as a measure for this limit for degradation. Because if we take smaller percentage, then sometimes we get the influence of, for example, water or something which is in there. And if we go far away to 20 or so, then the mechanism of decomposition can also change, and this can influence our final result. So 5% is, let's say, usually this limit which gives us best results. And so here, this is a graph of heating rate and different conversion at various various temperatures, and from this we can also estimate lifetime according to different temperatures. So temperatures are here. This is 1000 divided by temperature. So at 325 degrees Celsius, this will last, let's say, for at least 10 to 6 hours. If we use it at higher temperature, this will drop much more. And if we go to we can estimate that maybe this part will at 100 degrees will survive 10 years or 15 years or something. So to conclude, DSC and TGA are indispensable techniques for the characterization of polymers. They give us many interesting informations. We can use them to find some troubleshooting. Why do we have some problems? Maybe on processing, or maybe on also on the application of materials. And these are very important data for everyone who's working on polymer synthesis and polymer material development, polymer processing, of course, and applications as well of polymeric materials. Because, for example, if glass transition here, as I said yesterday, also is very important, because glass transition determines a lot on the temperature range where we use this material. And of course, what we also do is industrial espionage. So sometimes we get a sample from a competitor whose material is better than ours, and then of course we have to find out why it's so good. And those techniques, especially in a combination with others, for example, NMR, and so can give us some answers about that. So thank you for your attention. Any questions?
Just one comment and with a question combined. So you showed for PVC, the degradation starts at 250.
Yeah.
When I was a younger PhD student, we had this brown streaks starting at 200, 210.
Yeah, it's actually, I heard that the PVC starts to degrade about 70 degrees, but then degradation is very small.
Mm-hmm.
So if you have PVC on, let's say, 100 degrees, it will turn brown, but it will take maybe weeks or months.
Yes,
but here, yes, and if we measure it fast, then it looks like it degrades at a higher temperature. That's why this kinetics is important. And we measure at various heating rates, and then we can determine how it will behave maybe at 100 degrees.
And in injection molding or extrusion, you additionally create fear,
which also helps
pressure heating, and people mostly don't think that this reduces the onset of degradation.
Yeah. So if there is no questions, now we have lunchtime. So I would thank you all for participation and invite you again at 2 o'clock. We start with the afternoon session with some practical exhibition of measurement in the lab. Thank you and bye for now.